Okay, so what we're going to be talking about today is about precise and accurate measurements, random and systematic errors that happen in our measuring, and then minimizing those errors, uncertainties in the form of absolute, fractional, and percentage. And this is for analog and digital instruments. Now, uncertainties happen in every measurement. There will never be a time where it is absolutely perfect. And the reason why is that we could have measuring devices that are faulty, our techniques themselves are inconsistent or faulty. The nature of the measurement itself might be difficult, such as observations that change quickly with time, or possibly just human error. So there will always be uncertainties in every measurement. Now let's go ahead and begin our TNOTES for uncertainties and errors. And in order to begin with this, we have to talk about precision. So measurements can be either precise and or accurate. And the difference between the two can be a little bit confusing. So precision is how close together a series of measurements are to each other. It does not always mean that it is correct. For example, all of your measurements are together, so you think, oh, that's really nice. But it could be very far off from what the actual measurement is. In contrast, accuracy is how close a measured value is to the accepted value, or, in this case, the target. So here we have accuracy, but not really precision. So your arrows are not very close together, but they are hitting the mark. So here we have precision, not precise nor accurate, so it's off on all counts. Over here we have precision but not accuracy. And down here in the third picture we have accuracy but not precision. And of course the ideal is going to be to get to the point where the arrows are both accurate and precise. So our measurements are both accurate and precise. Now, let's take a look. Here we have an action figure, Optimus Prime, that weighs 363 grams. And I just wanted to show you an example of possibly weighing this object on 3 different weight scales to test whether or not it's precise and or accurate. So, for the first scale, we have 360 grams, 340 grams, 389, and 390 grams. This is equivalent to this picture here. The data is neither precise nor accurate. Everything is quite random. In the second scale, we have 377, 376, 375, 376. All of the measurements are very close together, but it's very far off from the 363 grams that we remember that Optimus Prime action figure weighed. This is precise but not accurate. And the last one, which is 363, 361, 363, 600, and 362. This is both accurate and precise to the measurement of 363 for the actual weight of the action figure. Now, there are 2 different kinds of errors that we talk about that you need to know. And these errors are called random errors and systematic errors. Random errors are just that. They happen without any knowing of what caused it. It's unpredictable and you can't tell why it happened. It could be caused by imperfect measuring techniques, or maybe your instruments are not calibrated correctly, which therefore would mean your data is going to be off when you take the measurements. It could also be something like environmental conditions because there's changes in the weather. So estimating even the measurements last significant figure. Remember, whenever you're taking measurement, you have to also make sure you are aware of the significant figure. By estimating, you are causing a random error, or you could cause an even greater random error. Reaction time when using a stopwatch. People measure differently. Maybe you're tired one day, and the other day maybe you're more, I don't know, maybe you had some caffeine, and so your reaction time is different. Reading measurements from different or even wrong positions can give you different points. Winds, clouds, they can cause temperature changes, and maybe the device itself, you could weigh an object like 3 times in a row and get 3 different values. Now, if random error is small, if the random error is small, then the greater the precision of the measurement. For systematic errors, these are where flaws could be in the equipment or even in the person doing the experiment. So their method could be faulty. There could be an error. Error actually does occur at every reading, so it's consistent. So you might not ever know that you have an error because all of your data is coming in and it seems like it's matching everything else. The values are bigger or smaller than the true value every time. The data is precise. It is not always accurate. Now, this is difficult to detect and it's very difficult to minimize. So for example, measuring tape that is stretched over time, you're going to continue to use it thinking that it's perfect, it's wonderful, but you don't know that it got stretched. So now each of your measurements is like a 0.1 millimeter over, or 0.1 centimeter, sorry. Incorrectly calibrated equipment. Maybe you're reading measurements from the different or wrong positions. Maybe you have bad eyesight and when you're doing a titration, you put too much liquid in and you miss the point that it turned pink. And so that's an error. Now, if systematic errors are small, the measurements are accurate. So this is what we're going for. Now, in order to minimize errors for random errors, you want to do multiple trials and then average the results, at least 5 trials. For systematic errors, it is not that easy because you don't know that your errors are off. Now, for unusual values, those should be checked and possibly excluded from the calculation of the mean if you're doing the averaging of the results. And then, of course, you may want to examine your measuring techniques and see if maybe you made an error in the angle of which you saw the measurement. So let's talk about range of uncertainty. So it's the area above and below the measurement that you find. So it's the best estimated value plus or minus some small amount of uncertainty. So the measurement equals the best estimate plus absolute uncertainty. So the best estimate plus absolute uncertainty is the true value. The true value is somewhere in there. So for example, 1.23 plus 0.05 grams means that the true value falls between 1.18 and 1.28 grams. So all I did was take 1.23 and I subtracted 0.05 to get 1.18 grams. And then I took 1.23 plus 0.05 grams to get 1.28 grams. So somewhere in this range between 1.18 and 1.28 grams is the true value of my object. Now there are 3 ways to represent uncertainty. Absolute uncertainty, fractional, also known, I believe you might call it relative in your chemistry class, and then percentage uncertainty, which is the same. It's just a different way to represent uncertainty. Now let's take a look at this graduated cylinder. Let's determine the absolute uncertainty for analog devices. Now, analog devices are non-digital devices. So pretty much the rule is half of whatever the smallest division is in your measuring device, that is your absolute uncertainty. So let's take a look over here and notice this is 41, 2, 3, 4. So we know that the smallest division is 1 centimeter, okay? So half of that smallest division would be 0.5 of a centimeters cubed, right? Because this is volume, liquid. So plus or minus 0.5 centimeters cubed is the absolute uncertainty. Now you have to measure. So now we have a measurement, if you're looking at this, is about 43.5 plus or minus 0.5 centimeters cubed. Now let's say, so pretty much what that means is that the measurement is at least 43 centimeters cubed, and at most 44 centimeters cubed. Now we just did this for analog devices. Now if we were trying to determine the absolute uncertainty for devices that are digital, it is a little different because this is more accurate. So it is the same value as the smallest division. Okay, so here we have 27.6 degrees Celsius. We know that we can go beyond 1 decimal place. So the smallest unit is 0.1 degrees Celsius. So 27.6 degrees Celsius plus or minus 0.1 degrees Celsius. Pretty easy. Digital is pretty simple. Okay, that is your absolute uncertainty, your absolute range of uncertainty, which is plus or minus 0.1 degrees Celsius. That means that this measurement is at least 27.5 and at most 27.7. Going back to our graduated cylinder, now that we know how to determine analog or determine absolute uncertainty for analog devices, now I want to have you determine fractional uncertainty, also known as relative uncertainty in your chemistry classes. In order to determine the fractional uncertainty, all you need to do is take the absolute uncertainty and divide it by the measurement that you have gotten. So that would mean you take 0.5 centimeters cubed and divide it by 43.5 centimeters cubed. The centimeters would cancel out and you would be left with 1 over 87. Okay, so if you were to divide 0.5 by into 43.5, because we're going to have 0.5 goes into 0.5 once, and then 43.5 divided by 0.5 would give us 87. This is a fraction. And so it's just a representation of the absolute uncertainty in a fraction form. And we call that fractional uncertainty or relative uncertainty. Okay, so when determining the percentage uncertainty, that is merely the absolute uncertainty over the measurement times 100, and that will give you the percentage. So take a look over here, and we know that each line is worth 1 centimeters cubed. So half of that would be 0.05, which is right here, 0.05 centimeters cubed. So in order to find the absolute uncertainty, you would just take 0.5 centimeters cubed, divide that by the 43.5 centimeters cubed, and the centimeters cubed crosses out, so you have multiplied by 100 in order to get an answer of 1.149%. Now, because 43.5% is 3 significant figures, and we don't have to take into account the significant figure of the uncertainty, our answer is 1.1. There we go. Now, one thing to note is that uncertainties of less than 5% in an experiment is desirable, but it's not always possible. So do your best in order to estimate your measurements and then see if whether or not your percentage uncertainty is near 5%. That's the ideal, but it's not always possible. So take a look at this pencil, and each line here is 1 centimeter, or 0.1 centimeter. So we know that the absolute is going to be plus or minus half that. So let's take a look. We have 7, 8, 8.1, 8.2. It's a little bit longer than that. So I'd say it's about 8.25 centimeters plus or minus 0.05 centimeters. That means that you have the measurement of this pencil could be anywhere between 8.20 centimeters and at most 8.30 centimeters. The fractional uncertainty, remember, is the uncertainty, the absolute uncertainty over the measurement that you had gotten. So it's 8.25 centimeters, and that is 1 over 165 when you divide 8.25 by 0.05. The percentage is merely 1 divided by, or 0.05 centimeters, divided by 8.25 centimeters, multiplied that by 100%, and you get an answer of 0.6060. And it does continue on for a while. However, because we have three significant figures here, we know that we just need to have three significant figures at the end. And this is a pretty good percentage, okay? So, read this measurement. This is a digital device, so we know that the absolute value is going to be 2 decimal places out. So it's whatever that digit is, which would be a 0.01 plus or minus 0.01 grams. Tack that on to the 335.49, and now you know that it could be 335.48 grams to 335.50 grams. The fractional is 0.01 over the measurement of 335.49 grams, and that gets you a fraction of 1 over 335.49. In order to find the percentage, feel free to stop this at any time to see if whether or not you get the right measurement. It is 2.9807 times 10 to the negative 5, which is pretty much the same thing. I'm not sure why I have it there twice. Alright, so that is the end of the video. Be ready to use this information in the next class. Review your notes. That's why you took them. So remember, in class, use your notes whenever we're asking questions or you need to refer back and try to remember things. So take care. Feel free to watch this video again, and we'll see you in class.